In the annals of aviation, few aircraft have captured the world's imagination quite like the Boeing 737. For decades, it was a symbol of reliable air travel, evolving through generations to meet global demand. Then came the 737 MAX, pitched as the most advanced iteration yet, promising unprecedented efficiency and comfort. It quickly became a paradox. How could a meticulously engineered aircraft, built upon a proven design, suddenly fall from the sky not once, but twice, within mere months? This wasn't a problem anyone explicitly foresaw, a hidden flaw lurking beneath layers of innovation and expectation. For much of the late 20th century, Boeing commanded a near monopoly in commercial aviation, particularly with its incredibly successful 737 Next Generation or NG series. But as the new millennium dawned, a formidable competitor emerged, Airbus. With its A320 series, Airbus began to chip away at Boeing's market share, especially with its fuel-efficient A320neo model. This competitive pressure created an imperative for Boeing. They needed a rapid response, an aircraft that could match the efficiency of Airbus's offerings without incurring the colossal costs and time associated with an entirely new design. The stakes were incredibly high. Boeing's strategy for the 737 MAX was clear: evolve, don't revolutionize. Rather than starting from scratch, the MAX was designed as an upgrade to the hugely successful 737 Next Generation. The core appeal would be its efficiency, primarily achieved by fitting larger, more fuel-efficient CFM LEAP-1B engines. This approach offered significant financial advantages, minimizing development costs and time to market. However, this seemingly smart business decision would inadvertently set the stage for a cascading series of technical challenges, eventually leading to a problem that nobody fully grasped until it was too late. The decision to integrate larger engines onto an existing airframe was not without its complications. The 737's low-slung design meant there wasn't much ground clearance for these bigger power plants. To fit them, Boeing engineers had to mount the new engines further forward and higher on the wing. This seemingly minor adjustment was a direct consequence of the upgrade philosophy. What appeared to be a clever engineering workaround would, however, subtly but significantly alter the aircraft's fundamental aerodynamics, creating a stability issue that would eventually demand a software solution nobody initially perceived as critical. The repositioning of the engines, while necessary for clearance, had an unforeseen side effect. It altered the aircraft's pitch characteristics, particularly at higher angles of attack. In certain flight conditions, especially when flying with the nose pitched up, the aircraft now had an increased tendency for the nose to pitch up excessively. This wasn't a catastrophic design flaw in itself, but it changed the handling characteristics from what pilots of previous 737 models were accustomed to. This subtle aerodynamic shift became the physical problem requiring an engineered response, a response that ultimately harbored a hidden danger. To counteract this new aerodynamic tendency and ensure the 737 MAX handled identically to the 737 NG, Boeing developed a software system, the Maneuvering Characteristics Augmentation System, or MCAS. Its primary role was to automatically push the aircraft's nose down under specific conditions. The intention was to make the MAX feel like its predecessor, simplifying the transition for pilots and, crucially, reducing the need for expensive and time-consuming simulator retraining. This system, designed to create continuity, would instead become the epicenter of an unprecedented crisis, a solution that held an unseen and deadly flaw. Initially, MCAS was intended to be a very niche system, activating only in extreme, high angle of attack scenarios, conditions rarely encountered in commercial flight. It was conceived as a subtle, behind-the-scenes adjustment, a safety net for a remote possibility. Boeing believed that because its activation was so infrequent and its effects so minor in normal operations, extensive pilot training or detailed documentation about MCAS wasn't necessary. This crucial assumption, that MCAS would remain a background player, blinded many to the potential severity of its interaction with other system failures, setting the stage for the problems nobody saw coming. Here lies one of the most critical elements nobody fully grasped until disaster struck. A significant design change was implemented. MCAS was allowed to activate at lower angles of attack, not just extreme ones. More critically, it was designed to rely on input from only one of two angle of attack (AOA) sensors. This single point of failure meant that if just one AOA sensor malfunctioned and sent erroneous data, MCOS could repeatedly force the aircraft's nose down, even when it shouldn't. This modification, a seemingly minor tweak, transformed a background system into a potential rogue agent, a problem that became lethal because it was never adequately highlighted. Boeing's commercial strategy hinged on minimizing pilot retraining for the MAX airline's preferred commonality. It saved them millions in training costs and allowed pilots to easily transition between 737NG and MAX models. This was a significant selling point against Airbus, which often required more extensive differences training. The design and implementation of MCOS, therefore, was intrinsically linked to this commercial goal. By making the MAX feel like the NG, Boeing aimed to avoid expensive simulator training requirements for MCOS, contributing to the system's obscurity, a decision whose full cost would soon become tragically clear. The consequences of this commercial drive were profound for pilots. They were largely unaware of MCOS. The system was not detailed in flight manuals, nor was it covered in pilot training materials. The philosophy was that MCOS operated entirely in the background, a benign automated helper that pilots didn't need to actively manage or even fully understand. This lack of information meant that when MCOS malfunctioned, pilots lacked the knowledge to diagnose the problem, let alone apply the correct emergency procedures. The very individuals meant to safeguard the flight were left in the dark about a critical system, a problem truly nobody anticipated the severity of. On October 29, 2018, the world received its first tragic warning. Lion Air Flight 610, a brand new Boeing 737 MAX 8, crashed into the Java Sea shortly after takeoff from Jakarta, Indonesia, killing all 189 people on board. The investigation quickly pointed to an erroneous angle of attack sensor. This faulty input caused MCOS to repeatedly activate, pushing the aircraft's nose down despite the pilot's desperate attempts to pull it up. It was a harrowing flight, a struggle against an invisible force, a pattern of failure that was just beginning to emerge, but whose true culprit remained largely unseen by the wider world. Less than 5 months later, on March 10, 2019, tragedy struck again. Ethiopian Airlines Flight 302, also a 737 MAX 8, crashed just minutes after takeoff from Addis Ababa, killing all 157 passengers and crew. The similarities to the Lion Air crash were chilling and undeniable. Again, an erroneous AOA sensor, again, MCOS repeatedly forcing the nose down, and again, pilots struggling against a system they didn't fully understand. Two identical catastrophes in such a short span of time screamed that this was not an isolated incident, but a systemic issue that had gone tragically, fundamentally, unseen. The second crash galvanized the world. Within days, governments and aviation authorities across the globe, led by China and Europe, took the unprecedented step of grounding the entire Boeing 737 MAX fleet. This wasn't just a handful of planes, it was hundreds of aircraft, a significant portion of the world's commercial fleet, rendered inoperable. The economic impact was staggering, but more importantly, it signaled a profound crisis of confidence in one of aviation's most trusted manufacturers. The once unseen problem was now starkly visible, demanding immediate and drastic action to restore trust and ensure safety. Investigations into both crashes quickly converged on MCOS. The flight data recorders revealed a chilling sequence of events. A faulty AOA sensor provided incorrect data, triggering MCOS to push the nose down. Despite pilots following established procedures for runaway trim, the system repeatedly engaged, overwhelming their efforts. The core problem, the single AOA sensor input combined with the system's unadvertised aggressive nature, became terrifyingly clear. It was a design flaw coupled with a knowledge gap, a lethal combination that had gone overlooked by almost everyone involved, from designers to regulators to pilots. As investigations deepened, a troubling narrative emerged. Boeing had prioritized minimizing pilot retraining requirements to make the MAX more attractive to airlines. This commercial imperative directly led to foregoing extensive documentation and simulator training for MCOS. It wasn't that Boeing actively sought to endanger lives, rather, a series of business decisions, driven by market pressures and a desire for competitive advantage, created a blind spot. The assumption that MCOS was benign and rarely active overshadowed the critical need for pilot awareness and robust safety protocols. The unseen problem was a direct consequence of these commercial priorities. The responsibility for the 737 MAX certification also came under intense scrutiny. The Federal Aviation Administration, or FAA, had for years utilized a program called Organizational Designation Authorization, or ODA. This program delegated significant certification responsibilities to Boeing itself. While intended to streamline the certification process, critics argued it led to a perception of inadequate oversight, where Boeing effectively self-certified critical aspects of the MAX, including MCOS. This systemic flaw in regulatory oversight meant that external checks that might have caught the problem were diminished, contributing to the nobody-saw-coming aspect of the crisis. The Boeing 737 MAX problem wasn't a singular failure, but a catastrophic convergence of technical misjudgment, commercial pressures, and regulatory shortcomings. A subtle aerodynamic change led to a software fix, MCOS. That fix, originally minor, was then altered to be more aggressive and reliant on a single sensor. Commercial pressures meant pilots weren't told about it. And regulatory oversight failed to catch these critical issues. Each step, individually, might not have caused disaster. But together, they formed a perfect storm, allowing a deadly flaw to propagate through the system, remaining unseen until it claimed hundreds of lives. After the global grounding, Boeing embarked on a monumental task to rectify the 737 MAX. This involved significant software updates to MCOS, ensuring it would only activate once, only if both AOA sensors agreed, and never overwhelm pilot inputs. Furthermore, enhanced pilot training and thoroughly revised documentation were mandated. This meant pilots finally received comprehensive information about MCOS and how to respond to its malfunctions. The industry learned that even seemingly minor software additions, especially those designed to alter fundamental flight characteristics, demand meticulous scrutiny and transparent pilot education. After nearly 2 years, and following rigorous review by aviation authorities worldwide, the Boeing 737 MAX gradually returned to service starting in late 2020. This return was contingent on all mandated changes being implemented and verified. For many airlines, getting the MAX back in the air was crucial for their operations, but the process was slow and fraught with the challenge of rebuilding public trust. The incident left an indelible mark on Boeing, the FAA, and the entire aviation industry, serving as a stark reminder of the profound responsibility that comes with designing, certifying, and flying passenger aircraft. The Boeing 737 MAX crisis stands as one of the most sobering lessons in modern industrial history. It revealed how a seemingly small design compromise, amplified by competitive pressures and regulatory blind spots, could lead to catastrophic consequences. The problem nobody saw coming wasn't a singular failure of a component, but a systemic breakdown, a failure to connect the dots between engineering changes, commercial goals, and pilot knowledge. While the MAX is now flying safely, the story remains a powerful testament to the constant vigilance required in aviation, and the enduring ethical questions about how industry balances innovation, profit, and the ultimate safety of human lives.